Hey class, this is Mr. Roberts at Shasta High School, and as I promised in class today, I am going to go ahead and record a video where I go through all the questions that were on the study team test that you took last week. You did get that test back last week, and we did go over the questions in class, but I want to give you a chance to kind of review this, step through this a couple times to help kind of consolidate some things that might be going on. So let's start in with this. One of the big ideas from this chapter was the fact that given some information, we should be able to come up with the equation of a line that fits that information. One of our key ideas is that we have a couple different forms for linear equations. The one we used almost exclusively in chapter 2 was the equation y equals mx plus b, where m is the slope, right? The coefficient of x. This is the slope of the line, the rise run pattern. And this value b right here, I'll double underline it. B is the y-intercept. That's the place where x is 0 and it's crossing the y-axis. So if we look at this first problem, it says, hey, this line, question 1, give the equation of the line that matches the given information. So for A, it says this line has a slope of 3 and a y-intercept of 5. Well, what's nice about that is we know the two things that we call parameters, the things we need to write down the equation of a line. One of them is we know the slope. The slope is 3, so I'd write y is equal 3 times x, and the y-intercept is 5, so plus 5. So this is the answer for A, y equals 3x and then plus 5. The next one says this line has a slope of 3/4 and goes through a point. So this one's a little bit more difficult because we don't have the y-intercept. We do have our slope, right? We know our slope m is 3/4. And we do have this equation we can work with, y equals mx and then plus b. And what we can do is go ahead and take everything that would go into this equation that we have, and the only thing that we're not going to have is we're not going to have the y-intercept. So this is a way for us to solve and figure out what the y-intercept is. So what I do is I identify this point, right? I've got an x value and I've got a y value. And then I'm just going to plug these things into the equation. So let's go ahead and start. So y, right? I'm starting here with y, and I see that my y value is 10. So I'm going to write 10 is equal to, the next thing I've got here is my slope, and I can see that my slope is 3/4. So for slope, I'm going to go ahead and write right below that equals 3/4. And the next thing I have here is x. And x is this value. I don't think this highlighter is going to work well. X, it's not working at all. X is this value. I'll underline it in blue. X is this value, and it's right there. So I'm going to write in place for x the value 8, and then plus the number b. So I need to multiply 3/4 times x. I can do that, right? 8 divided by 4 is 2, and 2 times 3 is 6. So this does give me 10 equals 6 plus b. I would remind you, if multiplication of a fraction by a whole number is a problem, right? I don't want you struggling with arithmetic. I want you struggling with the algebra. So don't forget, you can turn on the calculator and you just go, hey, I have a fraction, there's 3/4, and I'm going to multiply that by the number 8. It's kind of nice, whoops, times 8. It's kind of nice if you set this up, think about it, it's going to be 6, and then press enter. Just so the more you do that, the more likely you are that things like multiplication of a fraction by a fraction or a fraction by a whole number, it'll become clear to you what the pattern is, but go ahead and feel free to use your calculator if you feel like that's necessary. No problems with that. So I know subtracting 6 from both sides, right? 10 minus 6 is 4. And on this side, when I subtract 6, I'm going to get b. So I have the two pieces of information I need to write the equation of this line. I know the slope is 3/4, and I know the y-intercept is 4. So the equation is y is equal to 3/4 times x, and then plus the number 4. And if I want to check that, if I could check this by putting in 8 for x and just verifying that it does give me y is 10. All right, so that was part B. And again, there's a place to write this over here. I should write this down. Y is 3/4 x, and then plus 4 more. The next question says, this line go through point A and B. So I can see here that pretty clearly I can see the y-intercept, right? And moreover, I can follow this slope pattern. So if I was to go up 1 and then over 1, 2, 3, I could also go down 1 and then back 1, 2, 3. And I could see that that's going to hit exactly at the point 2. So I know that my y-intercept b is the number 2, and I know my slope is this rise of 1 and a run of 3. So my slope is 1/3. So I know both my slope and my y-intercept from this graph. So I can write the equation of that line. The equation is y is equal to 1/3 times x, and then plus the number 2. And then the last one, it says this line is represented by a partial table. So there could be more values, but here's a table of values. And again, I need to find the slope, and I just remind us that that's how much y changes divided by how much x changes for any particular point. What's nice is I've got lots of x and y's I could look at, so I can say, hey, y is at 16 and it goes to 22. How much did that change? I can take 22 minus 16, and I get that it went up by 4, 5, 6. Is that right? 6. So it changed by 6. X, on the other hand, it was the number 7, and it became 6. So I can take 7 minus 6, and I can get the change in x was 1. So when I look at these, right, I have a slope pattern that I have a change of y of 6 and a change of x of 1. So my slope is m is the number 6. Now, I'm just the same spot that I was up in part B. I don't know my y-intercept, right? I don't know what b is. So like up above here, we had to figure out what our y-intercept was. So I'm going to use the same exact strategy. What I'm going to go ahead and do here is write y is equal to mx plus b. And I can pick any of these points that I have. I've got lots of x's and lots of y's to choose from. I just have to pick a pair that go together. I'm going to go ahead and pick this pair. So I'm going to place in that y is the number 10, because that's the y value from that point, equals my slope, which is 6, or 6 over 1, and then times the x value from this pair. The x value is 5, so I'll put a 5 there, and then plus b. So what's b? 10 equals 30 plus b. And if I subtract 30 from both sides, 10 minus 30 is the number negative 20, and that's what b is. Again, any of the arithmetic, feel free to use your calculator. Just kind of practice and think about it when you do it. So what's our equation of this line? This equation is y equals going up by 6, so 6 times x, and then negative 20. All right, question 2 asks us to, given the input for several functions, identify the output. So we're told what's going into these functions, and the question is, what comes out? What are the outputs given these particular inputs? So both of these functions have different definitions, right? This first one, it is called f of x in part A, but it's defined as 3 times x plus 1 times the quantity of x plus 2. So there's some sets of parentheses here. I'm going to go ahead and place a value of x in each of these two locations. And I can see that it's a positive, x is positive 3. So if I put this right here, this is going to be x is 3 times another 3. 3 times another 3 would be 9, plus 1 more. And then the other set of parentheses, again, x is 3, right? That's the input. The input is 3, and 3 plus 2 more would give me a 5. So this is going to be times a 5. 9 plus 1 is 10. So what we're looking at here is 10 times 5. So the output would be the number 50. If 3 goes into this function, right, 50, the number 50 comes out of it. Your calculator would evaluate this perfectly. You could even store the value of x and look at this, right? So if you want to check your work, that's a good thing to do. You could do that as well. But we're going to move on to part B. In part B, our input is negative 4. Whenever I have an input that's a negative number, and especially if I see that I'm squaring or cubing or raising things to a power, I'm trying to be careful with that. So I'm going to go ahead and write open parentheses. I'm going to be placing a negative 4 in there. I'm going to square that. And then after I get that, I'm going to add 4 more. The reason why I do this is if I'm looking at my calculator, right, I need to be really, really careful. Where's that calculator? There it is. I need to be careful to evaluate this correctly. So if I'm evaluating this, I'm going to go ahead and say this is going to be in parentheses -4, and that's what's going to get squared. So this says very clearly I have a -4 times another -4, which gives me a product of 16. Now, if I was to type the opposite of 4 squared, if I was to type this is going to square only the 4, right? It's just going to be the 4 that gets squared, and then it's going to take the opposite of it, which would give me -16. But that's not what we have in this problem, right? This says we are to square x. When I look at this, it says you must square x. X is -4. It's the negative and the 4 together, so I'm squaring that whole thing, and I get an answer of positive 16. Of course, if I have an answer of 16, right, if that's what 4 squared is, and I add 4 more to it, I'm going to get an output here of 20. So 20 is the output. 20 is the output when I square -4 and then add 4 more. So the answer is 50 and then 20. Second page. On these, you can see the difference here. In question 2, you were given the input and asked to identify the output. In question 3, it says identify the input. So we don't know the inputs here. It's asking what input would produce the given output. So you can see that here we're wanting an output of 80, and here we're wanting an output of 17. So what I typically do is I take just the definition of the function, and this part right here is the definition of this function. This function says, it's 4 times x plus 2 times the quantity of x minus 20. So I write down the definition of the function, right? Again, I'm just going to write 4. Let me try to be neater. 4x plus 2 times the quantity of x minus 20. And I want that definition, I want that function to give me an output of 80. So if I set the definition equal to the desired output, what I can do now is solve this for x. I can go ahead and take all the steps to solve for x. The first thing I'm going to do is I'm going to rewrite this portion of it right here. I'm going to rewrite this so that there's no parentheses. Whoa. That's not what I wanted to have happen. So when I do that rewrite, this is going to become 4x again, plus this is going to become 2x, and then minus the number 40. So what just happened there was both the x and the -40 were multiplied by 2. I have to distribute a multiplication problem across different terms. So here I had a term of x and a term of -20. So both of those terms got a factor of 2. So that's a valid rewrite. On the other side, I've got 80 still. A quick rewrite here, 4x plus 2x would be 6 times x minus 40 is 80. If I add 40 to both sides, I would get 6x equals 120, right? 80 plus 40 more is 120. And then finally, x is going to be whatever 120 divided by 6 is. And I know 12 divided by 6 is 12 divided by 6 is 2, and I'm guessing 120 divided by 6. I'm guessing 120 divided by 6 is 20, but I'm going to go ahead and just double check that with my calculator. There you are. So I'll go ahead and hit 120 divided by 6, and I get an answer of 20. So I believe I figured out what x is. I think 20 is the input that produces the desired output. Now, I'm going to double check that by go ahead and I'm going to place the number 20 in here. So to check it, I can just type the following. I can say, I'll go 4 times 20, right? That's 4 times the input, plus 2 times the quantity of 20 minus 20. That's just 0, right? So I think this is working nicely because what I have here is 4 times 20, which is 80 plus 0. So yeah, that gives me exactly 80. So when x is 20, the output of that function is the answer 80. All right, and then part B, a similar problem on this one. It says, hey, we want this thing to produce an output of 17. So I follow the exact same pattern here. I'm going to take the definition of my function, 8x plus 1, right? fx is it's defined as 8 times the input plus 1 more, right? And I'm going to set that definition equal to the desired output. To solve for x, I would subtract 1 from both sides, so I get that 8x is 16. And then I divide both sides by 8, and I get that x is 2. So 2, right, should be the correct input. And that's easy for me to visually, just check. If 2 goes into this function, 8 times 2 is 16 plus 1 more is definitely 17. So the correct input would be 2. So if x is 2, right, when 2 goes into that function, it produces an output of 17. All right, we're now going on to part A. So in part A, like, we have all of our rules for powers kind of memorized, kind of in notes, kind of up in posters around the classrooms that we've created. This right here, I have y to the -4th times y to the 6th. And I'll just remind you, if we have some factors of y, let's say y to the 5th, and I multiply it by, let's say, 3 more factors of y to the 3rd, right, that becomes a total of y to the 8th, right? 5, 6, 7, 8. I'm just adding those factors up. So 5 factors of y times 3 more factors of y would be 8 factors of y. In this case, when I go ahead and combine these, I've got -4 plus 6, and -4 plus 6 does produce a positive exponent, so this becomes y to the 2nd power. So, and I'm just going to rewrite this part down below. So I've got 6 times x to the 5th power times y to the 2nd power. So that's our first answer. That's our answer for part A. 6x to the 5th, and then just y squared. Let's jump over to B. On B, you can see I've got factors of x in both my numerator and my denominator, right? And I've got in my numerator the number 21 and in the denominator 7. One of the things I can always do with those coefficients is I could just take and look at this 21 over 7 on my calculator. If I look at 21 over 7 as a fraction, it's just going to tell me that's 3. And if it's just 3, I understand that's 3 in the numerator. Another way I can look at that is this number 21 is 3 times 7, and I've got a 7 in the denominator. So when I rewrite 21 as 3 times 7, and I see that I have a factor of 7 in the denominator, that's gone, and I'm left with just the 3 in the numerator. So we got that part. There's going to be a 3 in the numerator. Now let's take a look at the x's, right? So I have 10 factors of x in the numerator and 8 factors of x in the denominator. There are more in the numerator, fewer in the denominator. So I'm going to write the one with the least number of factors. This is one approach. And I can mirror that in the numerator, x to the 8th, right? So I can see, the problem is that what I've written in the numerator is not what I started with, right? I need to make this look like x to the 10th. And to do that, I just need 2 more factors of x. So I can verify now that my numerator is exactly 10 factors of x. It's 8, it's x, 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 and then x, x, 2 more. So there are 10 factors of x in the top, and there's 8 in the denominator. I can clearly see this value of 1. So what I'm left with is 2 factors of x extra in the numerator, x squared. So I can write it as 3x squared over 1, or simply 3x to the 2nd power. This is 3x to the 2nd power. Let's go down to C. Okay, so for C, I have this is the same as this. It's the same as 4x squared to the 3rd power. I have 1, 2, 3 of these 4x squareds, right? 4x squared, 4x squared, 4x squared. Part of my answer is I've got this 4, a 4, and a 4. And I've got 3 4s as factors, right? 4 times 4 is 16, times another 4 is 64. 16 times 4, 16 times 4 is 64. Yes, I literally just typed that into my calculator to verify. 16 times 4 is 64. So I've got the 4 times 4 times 4, which is 64. And the other thing I have is I've got x squared, x squared, x squared. This is 2 factors of x, 2 factors of x, 2 factors of x, right? xx, xx, xx. My answer here is I've got 64 and then x to the 1, 2, 3, 4, 5, 6, x to the 6th power. 64x to the 6th power. And finally, let's look at D. So the thing that's scary about D, right, is we see these things, there's a 5 and there's an x, right? And we think, are they the same? And they're not the same, right? Don't confuse this with the following. Like if I had x to the third over x to the third, because they're both x to the positive 3, that's just equal to the number 1, right? And there's no more x's there. That's just equal to 1. That's not what we have here. We've got x to the negative 5th in the bottom. And we've observed this a lot, like what happens, how we can deal with the negative powers of x. One approach is to say, look, I can multiply this by the number 1. And in fact, the number 1 I would pick x to the positive 5 power. And the reason why I'm picking x to the positive 5 power is I understand if I multiply x to the negative 5th times x to the positive 5th, that is x to the 0 power, which just equals 1. So what I was able to do is I was able to turn this denominator into just the number 1. The reason why I can get away with this is I'm multiplying by x to the 5th over x to the 5th, which is 1. So I'm not changing the value of this expression. I'm just changing its format. In my numerator, you can see I've got a factor of 2, and then I've got x to the 5th, 1, 2, 3, 4, 5, and then 5 more factors of x, 1, 5, 6, 7, 8, 9, 10. So my final answer is 2 times x to the 10th power. And perhaps you see this and you've noticed this, right? If you have negative powers of, you can just take this and just bring those up into the numerator. But I'd like you to know why that's true, right? But if you've got x to the negative 5th in the denominator, that becomes x to the 5th in the numerator. So that is the answer to part D. Again, think about this, listen to it, keep growing, you're going to get better. So if I was to write down all my final answers, I've got 3x squared, I've got 64x to the 6th, and I've got 2x to the 10th power. All right, let's move down to part 5. 5 has 2 equations that we are asked to solve. This looks kind of scary. Let's see this. Let's do part A first. So over on the left-hand side, I can see that I've got an x plus another x plus another x. These are not being multiplied, they're being added. And if I have x plus x plus x plus x, that's 3 x's that get added up. So I'll just go ahead and write this is 3x, and then plus the number 5 is 2x plus 20. The next thing I could do is subtract 2 x's from both sides. This was just a rewrite, right? I just rewrote the left. Now I'm going to subtract 2x from each side. Over on the left-hand side, when I take away 2x, I get x plus 5. And over on the right-hand, sorry about that. On the right-hand side, when I subtract 2x, I get the number 20. Next, I'm going to go ahead and subtract 5 from both sides. And when I do that, I get that x should be the number 15. So x is 15 is my proposed solution. I want to remind you, one of the tools you have for checking things like this on the classroom calculators, right up here, is you can take the number 15, press enter, and then you can store that in x. So at this point, my calculator believes that x is the number 15. So if I put x there, it says, oh, 15, right? What that lets me do is take and type an expression like x plus another x plus a third x plus 5 more, and you can see it writes that that's the number 50. So when I do that, the left-hand side became the number 50. And then I have to see, hey, is that the same as the right-hand side? Well, the right-hand side is 2x, 2 times x, plus 20 more. And when I type that in, it says 50 also. So the reason why this is definitely the solution is because it makes both the left-hand side and the right-hand side equal to 50. So our answer here is that x is the number 15 because it makes both sides equal. It makes both sides 50. And then the final one right here is it's a good example of why it's nice to rewrite things. So one of the things I could do as a rewrite is this 22 divided by 2, that's just the number 11, right? So why write it like, make it look like a fraction? Let's just rewrite that as 11. The other thing that I've got is I've got x to the 4th over x cubed. One way to think about this is I've got 1, 2, 3, 4 factors of x in the top and 1, 2, 3 factors of x in the denominator, right? So x to the 4th is x, 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 x. X to the 3rd is x, x, x. If I take 3 factors from both the top and bottom and form this giant 1, right, you can see that this is just an x. So this becomes x plus 2x plus 11 is 44. If I combine these two, I get that 3x plus 11 is 44. If I subtract 11 from both sides, I get that 3x is the number 33. And if I divide both sides by 3, I get that x is 11. X is 11. So again, I'm going to check that. My calculator is still up here. Clear. I'm going to take, and I'm going to enter 11, and I'm going to store that as x. Boom. So my calculator now believes x is 11. So I can literally type this thing. I could go, hey, x to the 4th power over x to the 3rd power. That's ugly. Plus 2x. Oh no, I got to get out of my denominator. Sorry, delete, delete, delete. I needed to be out. There we go. Plus 2x. And then finally, plus, I'll do 22 over 2, 22 halves. This is supposed to be the symbol plus, though. I'm adding. Okay, when I go ahead and take and I add those up, right? X to the 4th over x to the 3rd plus 2x plus 22 over 2. My calculator says you get 44, which is great because what I can see is that the left-hand side becomes 44. The right-hand side already is 44. So that means that 11 is definitely my solution. So answer x is 11. Oops. And our last, I think we're on to our final page. Let's go to page 3. All right, page 3. On page 3, we have two expressions, and we're given values for our variables. We're given values for the variables a, b, and c. Probably much better if I get that calculator out of the way. I'm going to go ahead and color code my variables. So a, I'm going to mark as green. B, I'll mark as blue, and C, I'll do this kind of whatever color that is, peach or something. So this first expression says that I'm going to take whatever a is, right, and I'm going to multiply that by b squared. So b, b is, let me color code this. This is a, and I'm going to be multiplying that by b squared. So a times b squared, and then I'm going to subtract 16, and then I'm going to subtract, I still don't have my color coding right. A, I've marked green, B is blue, and then C minus this 12. And then I'm going to be dividing by 5 times what B is. I don't know if that was worth it at all. Let me just move on and do some substitution here. So where A is, I'm going to go ahead and write the number -4, and I'm going to have to multiply that by B squared, and then I'm going to subtract 16, and then I'm going to subtract 12 from that. And I'm going to divide that entire thing by 5 times 2. Now, if I look at order of operation, the first thing I'm thinking here is I've got to square this 2. So this is going to become -4 times 2 squared, or -4 times another 4. And then I've got minus, I can combine this 16 and 12. -16 minus 12 more is going to be a -28. And I'm going to be dividing all that by 10. If I look at that numerator, that is now -16 minus 28, still dividing by 10. If I look at -16 on my calculator and I'm going to subtract 28, oh, you know what? I should review this with you. So one of the things that we do struggle with sometimes is if you're entering a negative number. So I need negative, and then the number 16. So I hit, this is the opposite of 16. And now I can subtract the number 28. And I get the number -44 on the top. So this top is -44. And I'm going to divide that by +10. So 44 divided by 10 gives me an answer of negative 4.4. So I got options, right? I can write negative 4.4. Maybe I want to make that look like a fraction. That's the same thing as negative 22 fifths. That's the same thing reduced. And actually, you can write negative 44 over 10 as well, and those would all count as valid answers, right? And then the second one, B, same pattern going on. I've got A and I need to square it. I'm squaring A this time and it's negative, so I'm going to be very careful. I've got a negative 4 that I'm going to square plus 5 times what B is, 5 times 2, and then minus the number 12. So I'm looking at positive 16 plus 10, and then minus 12, which is what, 26? And if I subtract 12 from that, I get, I think I get the number 14. So I'm so sorry that that was all off the screen. You can see what I was doing there. So I am going to go and just run that expression on my calculator. So I'm going to take open parentheses. Here's my negative 4. I'm going to square that. And then I'm going to go 5 times 2, and then I'm going to subtract 12 from that, and I get the, I see my problem. My problem is that in this expression, oops, I was supposed to add this, so I'm going to do a quick insert and a plus. So this is correct now. Negative 4 squared plus 5 times 2 minus 12, and I get an answer of 14, which, big relief, because that's what I thought the answer would be. So negative or positive 14 is the value of that expression when fully evaluated. All right, second to the last question looks like this. Mr. Roberts and Mr. Woolard are racing their tricycles on the Shasta track. Because Mr. Roberts is clearly older and slower in many ways, he was given a head start of 4 meters, and he travels at a speed of 3 meters every 2 seconds. So we've talked about what it looks like to get a head start. Here's time, right? Time is on the x-axis. Time is 0. But when time is 0, I'm not starting at distance 0. When time is 0, I'm going to be way up here with a head start of 4. Right? So that represents my head start. And it says I'm going to travel 3 meters. So I'm going to go up 1, 2, 3 every 1, 2 seconds. Right? So I get to go up 1, 2, 3 every 2 seconds. I can do it one more time, up 1, 2, 3 over 2 seconds. So this is roughly the shape of my graph. I'm going to grab a ruler and just line this up on my screen here and go ahead and connect those points. And that's roughly the equation that models Mr. Roberts. And if I write that down as an equation, it's y is equal to 2/3 x and then plus the number 4. 2/3 x plus the number 4. I should not have that up there. Let me hide that. There we go. Y equals 2/3 x plus 4. Next, it says, let's look at Mr. Wooler. At the start of the race, Mr. Wooler does not pedal for the first 3 seconds. So think about this. This is kind of on your mark, get set, go. Don't move, don't move, don't move. So he stays completely still for 3 seconds. He's right here, 3 seconds into the race. And then at this point, we can see that he moves at a constant speed of 5 meters every second. So 1, 2, 3, 4, 5 over 1. 1, 2, 3, 4, 5 over 1. So we clearly see what's going on here with Mr. Woolard. Let me grab a blue color and draw his line. And this is one of those situations where, I don't know his y-intercept. I can see that this blue line goes way, way down, and his y-intercept is going to be some crazy negative number. Well, not crazy, but it's going to be a negative number, and I don't know what that is. So what I have to do is go ahead and try to figure that out. Now, here's how I'm going to do this, right? I know his slope, m, is the number 5. And I know that he's traveling through this point right here. And that point has an x-coordinate of 3, and it has a y-coordinate of 0. So I've got an x and a y at that point. Now, I could have just as easily used this point. This has an x of 4 and a y of 5. Or I could have used this point. This has an x of 5 and a y of 10. Any of those points would work for this process. I'm picking the ones that at 3 seconds, he's 0 meters from the starting line. What do? Well, I'm going to take the y equals mx plus b. I do not know the y-intercept. That's why I'm doing this. I'll place in my value of y, which is 0. I'll write 0 equals 5 times x, which is the number 3, and then plus b. So I've got 0 equals 15 plus b. And then finally, negative 15 is what b is. So if I'm asked to write Mr. Woolard's equation, it's going to look like this. It's going to look like y is equal to 5x minus the number 15. So that is the equation that models Mr. Woolard's speed. Or his, not his speed, it's modeling his path of travel. All right, so for our final question, we have one that involves dimensional analysis. We're given units and we're asked to go to different units. So it says, in another race, Miss Fifield travels at a speed of 12 feet per 1 second. So let's write that down. She travels 12 feet every 1 second. And we're asked to change this into the units of miles per hour. We want to go to miles per hour instead of feet per second. So we see this pattern that if I want, for example, feet to go away, because I do, the feet are in the numerator, and to cancel them out, I need to put a giant 1 expression that would have feet in my denominator. Now, we're asked to go to miles, and it turns out I do know that 1 mile is the same thing as 5280 feet. Giant ones like this that might be required for a problem, I'm going to share with you. They'll be up on the board and you can use those. But this is an important one, right? 1 mile is equivalent to 5,280 feet. What's nice about that is you can see already we've gone from feet per second. And now if you look at the units of the answer of this problem, rather, it would be miles per second. And we can see that because if I cancel out the feet here with the feet here and leave the numbers behind, what we're now looking at is some number of miles per second. Now I need to go to per hour. So the next thing I'm going to do is I want my seconds to go away. You can see seconds are in the denominator. So I'm going to put seconds in the numerator. And I know a giant one that involves seconds and minutes. In fact, 60 seconds is the same amount of time as 1 minute. But I have to do this again because I want the minute to go away. And I happen to know that so many minutes is the same thing as 1 hour, right? And how many? It's 60 minutes. So if you look at this now the rest of the way, right? Now, not only are the feet gone, right? But the seconds are gone. And not only are the seconds gone, but minutes over minutes, the minutes are gone. And the only units that remain in this entire problem is in the numerator, I've got miles, and in the denominator, I've got hour. So whatever this number is, it's a rate that is expressed in miles per hour. So I can write right here, hey, the number is miles per hour. But let's figure out what that number is. So I'll just grab my calculator real quick. Boop, there you go. Clear this. And I'm going to, probably the safest way to do this is just treat it as a fraction. So in my numerator, I've got a 12 times 60 times another 60. I didn't need to put the 1 there because multiplying by this 1 mile is not going to change anything. But I've got 12 times 60 times 60. And in my denominator, I've got 1 times 5280 times 1 times 1. So the only thing that needs to be in the denominator is 5,280. And I get an answer of 90 over 11. And if I kick that to a decimal, or yeah, if I kick that to a decimal, I got 8.2. So I'm going to say that her speed is about 8.2 miles each hour, right? So traveling 12 feet per second is the same as about 8.2 miles per hour. All right, class, that's it. I'll be in class early tomorrow morning if you're here for the first period 1, or you can swing by and talk to me at lunch if you have additional questions. We will have the notes that we talked about, and I'm rooting for you. I hope you do well. Talk to you later.